Okay, so today we're going to start chemical reactions. And at this point, guys, we won't be spending any more time on naming compounds. Okay, so if it's still something you're struggling with, that's okay. You just need to come in and get some help on it. Okay, here's why it's crucial you come in and get help. If you're still struggling with the naming, which again is okay, it's gonna start to snowball pretty quickly when we get into reactions. Because if you can't write the formulas and the names properly, you won't be able to get reactions right either. Okay, the naming and formulas are a very fundamental skill. Okay, and if you need help on that, come and see me, and I'll give you some help on it. But you got to be able to do them correctly. Otherwise, it is going to affect your ability to write and balance and stuff for chemical reactions. Okay, so for today, we are going to talk about the signs of a chemical change, look at the 5 basic types of chemical reactions, and understand how to identify each reaction type, okay, and look at how we write chemical equations. Okay, so in a chemical change, what are some signs that a chemical change or a chemical reaction has occurred? What would you be able to observe? I'm sure you know, so I'll wait. I have all the time in the world.
Smoke.
Okay, you could see a gas evolve. Smoke, yeah, okay, definitely could see a gas evolve. What else? Color change, yeah. Okay, usually bright colors, in fact, are a sign of a chemical reaction. Okay, what else? Temperature change could get warmer or colder. Some reactions are endothermic, okay, and would actually get colder. Okay. We talked about one of these the other day when we talked about solubility. Sometimes this gets formed in a reaction and falls out of the solution, starts with P. Sometimes we use it to describe rain or snow. All right, looks like 30 people need to go over their notes on solubility, because I guarantee you the word precipitate is going to be on your quiz tomorrow, and you will definitely need to know it. Okay? Precipitate being formed is also a sign of a chemical reaction. Right? So those are signs of a chemical reaction. Now, according to Dalton, when a chemical reaction occurs, okay, atoms are separated, joined, or rearranged. Okay, that's what he said, but they're not turned into the atoms of other atoms. Okay? That is why we see the signs of a chemical reaction that we are familiar with. Okay, bubbling and fizzing, or smoke is a gas being evolved. Okay, a color change. All of that stuff indicates that what has happened in that reaction has produced something new from what we started with. Okay, so I'll give you an example. Okay, if we have, let's say, this. Okay, if I mix these two things together, by the way, the things you mix together are called reactants. Okay, if I react those two reactants, okay, I will get a chemical reaction. Okay, and in that chemical reaction, I will produce the following things. Okay, did I make any new elements in that reaction? I didn't. I started out with lead and iodine and nitrate and potassium. Okay, and on the product side, incidentally, that's what these are called. These are the products. Okay, they're what's produced in the reaction. Okay, in the products, I have exactly the same elements. I don't have the same compounds because, as Dalton said, in this reaction, they were rearranged. Okay, they're all still there, but they've been rearranged. Okay, now, something else we have to be mindful of in a reaction is not that we can't just not, sorry, got a process. We can't produce new elements, we already know that, but we also can't have more or less than what we started with. Okay? It's called the law of conservation of mass, or the law of conservation of matter. Okay? I can't create matter, and I can't destroy it. Have you guys heard that law before? Okay, so in this reaction, okay, according to what I see here, on this side, there are 2 nitrates. But on that side, there are how many? Just 1. Okay, did I destroy matter then? Okay, if I had 2 nitrates on that side and I only have 1 on that side, I did destroy matter. There's a nitrate missing. It's gone. Okay, and similarly, here I have 1 iodine, but over here I have 2. I created matter. I'm God. Okay? I just did something godlike. I created something and I completely annihilated something else. No, I didn't. And I'm not. Just putting that out there just in case there was any confusion. Okay? But I'm totally not. Okay? I just haven't balanced this reaction yet. Okay? I have to make sure that I have the same amount of everything on both sides. Otherwise, I am going to break the law of conservation of mass, which you cannot break. Okay? It's not like human laws. It's a physical law. You can't break it. Okay? So, what I have to do is make sure that on both sides I have the same amount of everything. If I have 2 iodines over here, I have to make sure I have 2 here. But I can't just do this. If I do that, that compound isn't right anymore, is it? Okay? So I can't do that. I can't change the compounds. What I can do is I can change how much of that compound I have. Instead of having 1 molecule of potassium iodide, I'm just going to have 2 instead. Okay? Now, on this side, I have 2 iodines, because this 2 means multiply everything behind me by 2. And on this side, I have 2 iodines. So now my iodines are balanced. But what did I just do to my potassium?
I don't know.
Yeah, I mean, I made 2 on this side, but on this side I only have 1. So then I must need 2 of these. Okay? So when I have 2 of those, that not only takes care of the potassium problem, it also takes care of the nitrate problem. Now I'm obeying the law of conservation of matter, or mass. Okay? Now everything is balanced. I have 1 lead and 1 lead. I have 2 nitrates and 2 nitrates. I have 2 potassium, 2 iodine, and 2 iodine. Okay? Now everything works. Okay? Now I've balanced the reaction. That's what we're going to be working towards today. Okay? We're going to look at how Dalton's 4th point of his atomic theory, okay, kind of governs how reactions work. Okay? We're going to look at situations where atoms are separated. We're going to look at situations where atoms are joined, and several where they are rearranged. Okay? Most reactions involve a rearrangement. Okay? The joining and separated ones are pretty simple. All right. Is that making sense so far? I mean, beyond like, okay, Coderre just did a whole bunch of stuff and I don't understand any of it. Like, do you understand the premise? Not necessarily how to balance the reaction. Okay, so in a chemical reaction, the final products are chemically different than the starting reactants. And we can see that in the reaction I wrote here. Okay? My products are chemically different than what I started with. They contain the same elements, but they're rearranged so they're different. To give you an example, this is a clear solution. This is also a clear solution. Okay? This is a yellow solid, and this is a clear solution. Hang on guys, 1 sec here. I gotta take this guy. Okay, so as I was saying, so this is a yellow solid. So before the reaction, everything's clear. But after the reaction, I got something yellow. Do I get a color change in that reaction then? Okay, and this is a solid. Everything before, there were no solids. Okay, these are the signs of a chemical reaction are what they are because when a reaction happens, we make something new. Okay, not new elements, but new compounds, and they have different physical properties. Okay, those same physical properties that we're going to use tomorrow to identify unknown compounds. Okay, for example, if lead 2 iodide was one of our unknown samples, you would see a yellow powder. Okay, in the jar. Spoiler alert, it is not. Okay, but that would be its physical properties. It would be an ionic compound, and it wouldn't dissolve very well in water. Okay, but its solution, whatever bit of it you get, would conduct electricity. Okay, everybody kind of follow me there? So the reason we see the signs of a chemical reaction that we are familiar with is because when a reaction happens, new things with new physical properties are produced. Okay? And so there are changes. Now, the thing about a chemical reaction is this. It's not naturally going to go backwards. Okay? For example, a campfire is a chemical reaction. Can you unburn the wood? No. Okay? You cannot reverse that chemical reaction. It's done. Okay? Now, are there some chemical reactions that are reversible? Yes. Okay? But they require energy. Reactions happen because they're naturally moving kind of down what we call like kind of the scale of enthalpy. Okay? So they naturally occur in a certain direction. Okay? Every day you use a chemical reaction to power your cell phone. Okay? That reaction happens and releases energy that powers your phone. And then at night, or if you use your phone a lot, 3 or 4 times a day, you plug it in, okay, and you make the reaction go back the other way. You recharge the battery. You reverse the reaction. Okay? Now, is there a set number of times you can do that? Yeah. You can't continue. Your cell phone battery is not going to last forever. Okay, I had one phone that I had for a very long time. I think I had it for like 4 or 5 years. Okay, and I put 2 different batteries in it. Okay? They just don't last forever. Now, granted, one time I did drop it in the river, so that battery was kind of shot. But after that, the other one I had to replace it. They only have so many cycles. Okay, eventually that reaction won't go back the other way. Okay, making sense? Okay. All right. So. Evidence of chemical reaction: color change, odor change, state change, energy change. That would mean it gets hotter or colder. Okay, and we get things that are chemically different than our starting reactants, and thus we see those changes. Okay, because we're producing something that is new. Okay, questions so far? Okay, so the first kind of reaction we're going to talk about is the simplest one. Okay, and when Dalton was describing what happens in a chemical reaction, the first thing he said was atoms can be joined. A synthesis reaction is the joining of 2 atoms, okay? Well, 2 or more atoms, okay, to form a compound. Okay, so a synthesis reaction, 2 or more elements react to form either an ionic or a molecular compound. Okay, so a very simple example, okay, could be this reaction here, where we have magnesium reacting with oxygen, okay, and it's producing magnesium oxide. Yes, sir. Okay, now, the S's and the G's, you're not going to have to worry about those in Science 10. I sometimes write them out of habit. Okay, they're telling you the state. S stands for solid, okay? G stands for gas. If you see an L, it's a liquid. And if you see AQ, it means it's something dissolved in water. It's an aqueous solution, okay? And so AQ stands for aqueous. You're never going to have to write those things, but they basically require you to look on the periodic table and see the melting point, boiling point, whatever, and decide what state it would be in. Okay, just so you know, the periodic table is set up in such a way that you can tell the state at 20 degrees Celsius from the color. Anything that's yellow is a solid. Anything that's blue is a gas. Okay, anything that is pink is a liquid, and the greens are what we call non-metallic solids. Okay, so the yellows are metals, and the greens are still solid, but they're just not metallic. Okay? Again, you're not going to have to put the states on your reactions. All right, so a couple of examples here. Okay, we got the magnesium one, and then if we were diagramming a synthesis reaction, okay, we would see two single atoms of potassium reacting with one molecule of bromine to produce two molecules of potassium bromide. Okay, why did I say one molecule of bromine? Right, okay, remember the other day I told you there's a few elements that will bond to themselves. They are the molecular elements. So now those become important. When we talk about reactions, we need to know which elements are molecular elements, and that means that they bond to themselves. Okay, so just as a quick review, okay, those elements are, okay, everything in group 17. Okay, everything in group 17 comes as a 2. F2, Cl2, Br2, I2, At2. Okay, they all come as a 2. They pair up with themselves. Okay, as do nitrogen and oxygen. Okay, so this 7 right here. Okay, and in fact it is actually 7. The 7 in the 7. Okay, are 2s. Right. Hydrogen is a 2, and it comes as a 2 when it's by itself. Right, and then you got the 2 oddballs. And the 2 oddballs are phosphorus, which comes as a 4, okay, and sulfur, that comes as an 8. Okay, you are required to memorize those. If you're marking them on your periodic table right now, I probably should have said this before, okay, that's not one of the things you're allowed to know on your periodic table. Okay, that's one of the things you have to memorize. Okay, you're not allowed to mark it on there. Right, if it's seen on there, then you'll get a fresh periodic table on the test. Okay, so you do need to know those ones. All right, so bromine is a molecular element. Right, what does that mean? It just means it comes as a pair. It doesn't really change what happens reaction-wise. Okay, in the reaction, those 2 atoms are separated. Okay, and they're put together in those elements. Yes. Okay, questions on that? Okay, so in a synthesis reaction, 2 elements go together. Now, is this reaction balanced? Did I create or destroy any matter in that reaction? I didn't. Okay, so at this point it's important to know how these things are written. Okay, this 2 means there are 2 potassium atoms. Okay, so if you see a big 2, or a big 3, or a big 5, okay, whatever it is, it's big like that one, okay, it's a coefficient. It means there's this many of this. Okay? When you see a little 2, or a little 4, or a little 8, or whatever the number happens to be, if it's subscript, like this, that means they're bonded together. Okay, so subscript numbers indicate these things are bonded together. Okay, big numbers indicate that they're separate. Right, so in this case, okay, this is 2 atoms separate of potassium. This is 1 molecule containing 2 bromine atoms. This is 2 molecules of potassium bromide. This would be molecule number 1, and that would be molecule number 2. Okay, everyone follow the difference there? Okay. The reason we have those different numbers is because I can't just go like that and say there's 2 potassiums, because that doesn't mean the same thing. That means those 2 potassiums are bonded together. Okay, I need to say I have 2 atoms of potassium that are separate. So is there a lot to know when you're reading a reaction? It's almost like learning another language. Okay? You're reading sentences in chemistry, okay, as opposed to English. All right, second type of simple reaction is the exact opposite. In a synthesis reaction, atoms are joined. Okay? In a decomposition reaction, they are separated. Okay? So it is the decomposition of a compound. Right? That's what's going on. Okay, so in a decomposition reaction, at least a simple decomposition reaction, a compound breaks down into its elements. Okay? In a complex decomposition reaction, a compound can break down into several compounds, okay, depending on how big it is. We don't deal with those, okay, in Science 10. Okay, so this reaction here, okay, H2O gives hydrogen and oxygen. Okay, how many people have seen The Martian? Okay, how many people read the book? Book's better. Read the book. It's awesome. It was the first book I ever got on Kindle. I got it for free. That tells you how old I am. A little bit. Okay? It's awesome. It's a great book. Anyway, in The Martian, there is a point where Mark Watney is trying to make rocket, or he's actually taking rocket fuel, and he's splitting it. Okay? He's trying to get the hydrogen and the other way around. He's trying to split. He's trying to make water. I don't remember now how that went. Anyway, he's using the rocket fuel, and he's splitting, okay, the water into hydrogen and oxygen, and that's why he blows himself up, okay, because he gets all this hydrogen gas, okay, which he's not really wanting, and he's getting all this oxygen that he is wanting, okay, so he can like keep breathing or whatever, and he blows up the part of the have, and he's got no eyebrows, and he's kind of frustrated with himself. Okay, that's this reaction. Okay, it's the reaction that essentially makes rocket fuel. Okay. All right, and then for this one here, okay, we've got 2 molecules of nitrogen triiodide, and it's breaking down into nitrogen gas and iodine liquid. Okay, now, when it breaks down into 2 of our molecular elements. Yes? Nitrogen's a 2, iodine's a 2. Okay? This is where reactions gets tricky. I have to remember that. Okay? I have to remember when I'm writing this reaction that the nitrogen that's produced comes as a 2, and the iodine that's produced comes as a 2. Okay? If I don't remember that, I won't write the reaction correctly. Okay? And as I was using the learning a new language analogy, it would be like you're talking to somebody and then you use like 2 words that are wrong and they misconstrue the sentence and they think you've said something really offensive and you are asking for a slice of bread, okay? But they think that you wanted to, I don't know, do something horrible, okay? Because you messed up 2 words. That would be the equivalent of forgetting that these 2 things are molecular. It would change the context of the sentence, okay, or the reaction in this case. Okay, so in a decomposition reaction, all right, we started out with 2 molecules of nitrogen triiodide, okay, and from there we went to 1 molecule of nitrogen that contains 2 nitrogen atoms, and 3 molecules of iodine, each one containing 2 atoms of iodine. Okay, in the end, do I have the same amount of matter on both sides? Okay, well, here's how I find out. Okay, this 2 means there's 2 of these, 2 nitrogens then, right? 2 times 1 is 2. Over here there are 2. Okay, 2 times 3 is 6. 3 times 2 is 6. I'm good. Okay, it's all balanced. All right, everybody good with that one? All right, now. So as I was saying here on your periodic table, okay, you've got the 7 here, okay, that are your 2s, okay, you've got phosphorus as a 4, sulfur as an 8, okay, hydrogen also coming as a 2, right, you just have to remember those are your molecular elements. All right. Now, I'm going to give you about a 5-minute break here, and then we're going to talk about combustion reactions. So 5 minutes within the classroom, answer all your burning snaps there. So combustion reactions are probably the trickiest ones, and it's because they have their own rules, okay? we're going to look at 5 reaction types. 4 of them obey the same rules. Combustion has its own. Okay? Now, combustion still obeys Dalton's atomic theory. It's just the rearrangement of elements. Okay? But they behave a little bit differently. So when you burn something, you are causing a chemical reaction to occur between whatever your fuel is, right? Usually a hydrocarbon of some kind, and oxygen. Okay? It is basically the rapid oxidation of your fuel, and that is going to release heat. Okay? The byproducts of combustion are always, and when I say always, I mean always, the same 2 things: carbon dioxide and water. Okay? If we have complete combustion, those are the only 2 products. Now, complete combustion is very rare because fuels always contain impurities and additives and things like that. Okay? So there's always some other junk that gets produced, but we're not going to deal with that. We're going to deal with ideal combustion reactions where only carbon dioxide and water is produced. What's something else that gets produced in combustion that's dangerous? You certainly don't want it to get into your house. Carbon monoxide. Okay? That comes from the imperfect combustion of fuel. Okay? Gasoline, propane, natural gas, doesn't matter. They all produce a little bit of that because no combustion is perfect. Okay? Carbon monoxide is that colorless, odorless, okay, gas that bonds to your hemoglobin and prevents hemoglobin from transporting oxygen. You get tired, you fall asleep, and you possibly don't wake up. It's scary stuff. Okay? All kinds of safety is designed around reducing that. The way your hot water tank and your furnace are vented out of your house, okay, are designed to prevent carbon monoxide from building up in your house. The reason your garage door, if you have a garage, automatically closes the door. Okay, the little, if you have a garage where you walk out into the door, that door is on a spring. It always slams shut. Okay, that's because that door needs to be closed in case your command start accidentally starts your car. Okay, you don't want the carbon monoxide to come into the house. Okay, all of those things. Okay, even the way, anyone ever look at how the pipes come out the side of their house? Okay, when you own a house when you're older, this is something you want to check when it gets cold. Okay, your furnace and hot water tank are vented outside your house, and if you have an older home, they may go into a right angle that goes downwards. Okay, that can be dangerous and is no longer code for building because when it gets really cold, all the water vapor, okay, which comes from combustion, condenses and freezes and builds an icicle upwards that can actually go up into that pipe and block it, okay, which would then not allow the exhaust gases, carbon dioxide, water vapor, and carbon monoxide to get out, okay, and they would go back into your house. Your furnace usually has a pressure sensor that detects that the exhaust is not getting out and will shut the furnace off. That's, Mr. Dickey had that problem just last week. Okay? He came to school and he was really frustrated. It was his birthday and his furnace quit. I mean, that's a lousy birthday present, a broken furnace. And they just had it replaced. Okay? And what had happened was some ice had built up because the pipe wasn't run correctly, okay? And the sensor had shut the furnace off. So he and his family stayed safe, not warm, but safe, okay, until they got the furnace fixed. So all of those little things. You always want to go up when it's cold as a homeowner and check. Okay? I know I went out during the cold snap. Okay? My pipe comes out and goes into a T like this, and on both sides of the T, I had icicles that were within a couple of inches of the pipe itself. Okay? Just go up and kick them off, okay? Because you don't want them to go into the pipe. Yeah? Something to watch for. Because water is a byproduct of combustion. Okay? You've probably seen that on a cold day when you're behind the car in front of you and there's water dripping out of the exhaust pipe. Okay? On a cold day, it's cold enough that along the length of the exhaust system, the water vapor will condense back into a liquid. Okay? And the force of the gas will just shoot the water out. All right, so in a combustion reaction, okay, you have carbon and hydrogen, a hydrocarbon, okay, reacting with oxygen, producing carbon dioxide and water, right? This is propane, C3H8, okay, so it's what you would use in your barbecue, okay, propane gas. And it's reacting with those oxygens, okay, let's see if this reaction is balanced. How many carbon are there here? 3. How many over here? Still 3, right? That big 3 means there are 3 carbon dioxide molecules, and each carbon dioxide molecule has 1 carbon in it. Okay. How many hydrogens? 8. Okay. How many over here? 8. Hey, how many oxygens here? 10. Okay. How many here? 4. Plus 6 more. Okay, the oxygen ends up in 2 places in that. Is that okay? It happens quite a bit actually. Okay, you always have to look and make sure that an element isn't in more than 1 place in the products, because it can happen, especially if you get 3 products or 4 products. Okay, it can get spread out between them all. Okay, so balancing a combustion reaction can be tricky because it has its own rules. 2. So it's not like there's like 10 rules or 10 commandments for balancing chemical reactions. There are 2 rules. Okay? And the first rule is that you balance in alphabetical order. So we should probably write these rules down. Okay? These only apply to combustion. Okay? So the first rule of balancing combustion reactions is to balance in alphabetical order. Okay, that would be carbon, hydrogen, oxygen. Okay, balance carbon first, balance hydrogen second, balance oxygen last. Okay. The second rule is what I call the rule of 2. If you're a Star Wars fan, you know what that's referring to. Okay? Rule of 2, okay, is what Yoda said about the Sith. Okay? Now, when we're talking about combustion reactions, it works a little bit differently. Okay? The rule of 2 goes like this. If an even number of carbons you have, balance with the 2 you must. Okay? So, by the way, that's a little sound bite that's recorded for you later. Now, I'll explain what I mean by that, because that rule out of context probably doesn't make a lot of sense, but I'll explain what it means here in just a minute. Okay, can I scroll up just to show you the reaction? Everyone's done with those? All right, so here's what I mean by an even number of carbons. So let's say I have this reaction here. Okay. In all other reaction types, except combustion, our balancing rules are simple. You start with the biggest number and balance it first, and then go from there. It's easy, works pretty much every time. Okay? But if I do that with combustion reactions, it doesn't work. Okay? And start with hydrogen and the whole thing would get messed up. It's why it has its own set of rules. Okay? So, I'm going to balance this alphabetically, and I'm going to start with carbon. How many carbons are there here? 4. Okay, so what do I need to put in front of carbon dioxide to make 4 carbons? 4, right? This means 4 times 1. There's only 1 carbon here. Okay? Next thing alphabetically is hydrogen. How many hydrogens are there here? 10. Okay, how many over here? Okay, what times 2 will give me 10? 5. All right, so if I put a 5 here, okay, now my hydrogens are balanced. But here's the problem. Now I have how many oxygens here? 5, right? 5 times 1 is 5. Plus, how many here? 8. All right, 5 plus 8 is 13. What times 2 is 13? 6.5. Can I have 6.5 molecules? No, right? That was another one of Dalton's points. They combine in whole number ratios. You can't have a half. Okay? If I do that, I'm going to write 6.5 here. That doesn't work. That means I have 6 whole oxygen molecules and then a single atom after that. Oxygen doesn't come that way. Okay? And that's not what the reaction says. So, to get rid of a half, I multiply by 2. If I multiply this whole reaction by 2, I'll have twice as much of everything. And what's 2 times 6.5? 13. Is that a whole number? Yeah. It's also a prime number. Okay? But it's a whole number. All right, so that's what I'm going to do then. I'm going to start this thing over again. But now I'm going to do what Yoda says. And I'm going to start balancing with a 2. Okay? I have an even number of carbons here. 4 is an even number. So I start my reaction with a 2, because this happens anytime there's an even number of carbons. You'll get that 0.5 problem. Okay? The way to get rid of the 0.5 problem is to just double everything. So what's 2 times 4? 8. All right, so then I go over here, and I put in 8 there. Okay, how many hydrogens do I have? 20. Okay, what times 2 will give me 20? 10. All right, now I look at my oxygens. 10 times 1 is 10, plus 16 is 26. What times 2 is 26? 13. Okay, now I could balance it, and I didn't get any decimals. Okay, so when you have an even number of carbons, you start your balancing with a 2. If you don't, if you have this, okay, if you have an odd number of carbons, you don't need to do that. Okay, if I do this one, and I'll just do it quick, okay, I got 5 carbons here, so now I got 5 here, I've got 10 hydrogens, now I've got 10 there. Whoops, sorry, I wrote that compound wrong. That's supposed to be 12. Forgot my organic chemistry for a sec there, guys. Okay, C5H12, so there's a 6 here, okay? Now, when I do my oxygens, 6 times 1 is 6. Plus 10 more is 16. 8 times 2 is 16. I can start with a 1 if there's an odd number, but I have to start with a 2 if there's an even number. Okay? If that intimidated the heck out of you, that's okay. We're going to spend a lot of time on reactions. You're going to get lots of practice. Okay. All right, so in a combustion reaction then, okay, combustion reactions are very obvious. They always have CO2 and water as a product, and they always start with carbon, hydrogen, and oxygen. Okay? They just look very different than all the other reaction types that we're going to go over. Okay? Obviously, they're not a synthesis reaction. They don't start with 2 elements. Okay? They're not a decomposition reaction that starts with only 1 compound. Okay? And they're not either of the 2 replacement reactions that we're going to look at next. Okay? All right. Okay, so single replacement and double replacement reactions. They're both replacement reactions. And replacement reactions only involve ionic compounds. Okay, so these reactions, all the compounds in them will be ionic. There will be no molecular compounds. Okay? There might be elements, but there will only be ionic compounds. Because there's a switching that has to go on, a replacement, okay, a rearrangement according to Dalton, that has to go on in these reactions. And that only works if you're swapping positive and negative ions. So replacement reactions always involve the trading and replacement of ions, okay? Okay, so the first kind is a single replacement reaction. In a single replacement reaction, an element will react with an ionic compound. When that happens, the element will replace the part of the ionic compound that it is similar to. Is copper a metal or a non-metal? It's a metal. That means it's going to replace the metal in the ionic compound. Right? So in a single replacement reaction, this element jumps into the compound and kicks out the part that it's like. Okay? And that part ends up by itself. Okay? So the analogy used here, okay, is it may be a little bit old-fashioned now, okay, but it's like this dude is standing by himself and he sees these two people together, okay, and he likes her, so he like rolls this dude, okay, and takes off with the girl, and this dude winds up by himself now. Okay, now chemistry is very old-fashioned, so a dude has to replace a dude, okay, but that's like not a comment on modern day stuff, it's just chemistry is old-fashioned. Okay, everybody with me there? So in a replacement reaction, a metal has to replace a metal. A non-metal has to replace a non-metal. They can't switch, okay, because they have different charges. Okay, I can't put two negatively charged things together in a compound, but I can take a positively charged thing and replace the positively charged part of that compound. Right? So it has to replace the thing that has the similar charge. Metal replaces metal, non-metal replaces non-metal. All right, so in this reaction here, what gets produced in the products? What's by itself over there? What's Ag stand for? Silver. Okay. When this reaction happens, you get silver, solid, metal. Okay. Don't think you're going to get rich on this reaction. Silver nitrate is really expensive, okay, because, well, it has silver in it. So you're not getting ahead by it. Unless, of course, you stole some, but that's not ethical. Okay. So what we do with this reaction, what it looks like is if I took like an old penny, okay, and I dropped it into a solution of silver nitrate and left it overnight, when I came back the next morning, the penny would be plated in silver. That means it would be covered in silver. The silver would start to replace the copper on the surface of the penny. Okay? So you'd have a silver penny. Okay? Just on the outside, you'd be actually able to peel it off with your finger. Okay? Little flakes of silver. Right? So if you had like a whole bunch of copper wire, you could throw it in silver nitrate, and the next day you'd have a whole bunch of silver plated out on the copper. Okay? Sort of makes sense? Reactions are weird. All right. Is this reaction balanced? How many copper do I have here? 1. How many copper here? 1. How many nitrates here? 2. Right? There's a bracket around the nitrates. This 2 outside the bracket means there's 2 nitrates. There are 6 oxygens and 2 nitrogens, but we just go with nitrate. There's 2 nitrates. Okay? Are there 2 nitrates over here? Yes, because there's just 2 in front of this compound. Okay? Are there 2 silvers here? Are there 2 silvers over there? Okay. All right, so that reaction is balanced the way it's written. So in a single replacement reaction, okay, an element reacts with an ionic compound, replaces the part of the ionic compound that it's like, and your products will be that replaced thing by itself and a new ionic compound. You only ever get ionic compounds. Now, it could work this way as well. Okay, does this look like a single replacement reaction as well? Okay? I have an element, chlorine, okay? It just happens to be one of those molecular elements, but it's an element, okay? Reacting with magnesium oxide, which is an ionic compound. It has a metal and a non-metal. Okay? Who is the chlorine going to replace in this compound? The oxygen, because the oxygen is the non-metal. This is a non-metal, that's the non-metal, so they're going to replace, they're going to switch, right? So what's going to happen is, I'm going to get oxygen, and magnesium chloride. What's that?
How do you get two oxygen though?
Well, because oxygen is one of our special elements. When it's by itself, it always comes as a pair. Because you're reading my mind. Stop doing that. Okay. There's dangerous things in there. So when I have a replacement reaction happen, I could possibly produce special elements. Okay? This is where I have to remember what elements are special. If I forget that, I write this reaction like this, and it's wrong. When I try to balance that now, I'm going to put the wrong numbers in. Okay? Because I'm going to go and I'm going to do, so I'm going to have a 2 in front of this, okay? And then I would have to put a 2 here. Actually, if I was balancing this one, I would leave it this way, and it would be wrong. Okay? That's not what happens in this reaction. Okay? This means I need 2 of these, okay? 2 of these, and 2 of these. Balance is different. Okay? All right. So it could be a metal by itself or a non-metal by itself, but the process is still the same. They replace the part of the compound that they're like. All right? Everybody okay with that? Okay. Now, double replacement reactions sound more complex, but are actually easier. Okay? In a double replacement reaction, 2 ionic compounds react. Just like the first one I showed you where we were talking about the lead and the potassium and that kind of stuff. Okay? In a double replacement reaction, all you ever do is this. Swap the metals. So you get 2 different ionic compounds on the other side. Okay? In a double replacement reaction, okay, it's 2 ionic compounds, and we got to make 2 different ionic compounds. The only way to do that is to switch the metals, so I get metal, non-metal, metal, non-metal on both sides. I can't end up with 2 metals together. I can't end up with 2 non-metals together, because then I don't have ionic compounds, and my charges aren't balanced. Okay. All right. So in this one, is this reaction balanced? How many calcium here? How many? Just 1, right? There's no number in front of this. That 2 only applies to the chlorine. So there's 1 calcium. How many calcium here? Still 1. How many carbonates here? 1. Okay. How many carbonates here? 1. 2 sodiums. Are there 2 sodiums over here? Okay. 2 chlorine. 2 chlorine. We're good. That reaction's balanced. Okay. That's the kind of stuff we're going to be working on, is being able to identify a reaction, being able to write it in either word or formula form, so writing all the names of these and balancing the reaction. And eventually, we'll get to the point where I only give you the first part, and you have to predict the products. Okay? Right now that probably sounds really scary, but trust me, because of Dalton, it's not. You can only end up with the same stuff on the other side. You just have to rearrange it properly, right? You can't create any new atoms. You just have to rearrange what you had to start with. Okay, we'll stop there because that's a lot. Okay? That's a big lesson. It's a lot. Okay, tomorrow, quiz lab. Okay, I will post the quiz. Here's what's on the quiz for tomorrow. There's going to be some solubility stuff and some naming stuff. None of the reaction stuff. Okay. So solubility, maybe a little bit of properties, and a little bit of naming, okay? But no reaction stuff because we just started that.